Hi, welcome to Breadth First Search. This is used to find out shortest path to all the vertices available in the graph. Here the graph is given with set of vertices and edges, 8 vertices and 10 edges. So in directed graph, when you are selecting the source vertex, it should have path to all the vertices through other vertices. That should be the criteria. For undirected graph, you can select any vertex as a source vertex. Here for getting the input data for graph, we can use adjacency matrix or adjacency list to know the adjacency nodes of selected vertex, and it will use queue data structure. Initially we are taking the graph with number of vertices and edges, then we are using the queue data structure which is having which is going to have the selected vertex and its adjacency nodes in the given graph. So front pointer denotes the node going to delete or access from the queue, and rear pointer used to store the data or enqueue the data into queue. Here this table shows number of vertices connected or visited in the graph. Right, first we are going to select the vertex that is going to be root vertex. So here we are going to select the root vertex as a D. As of now, number of visited nodes are nil. So D is going to be selected as a source vertex, I mean starting vertex, that is a root now. D is not yet visited as of now. So it is going to be enqueued into the queue. Then after enqueued, we are going to mark that D is connected. So now we are going to mark that D is connected. Then we are deleted that D from the queue. So we are deleting that D from the queue. After deleting, we are finding the adjacent nodes to the D. Adjacent nodes to the D is C. So direct edge is there, and here also direct edge is there. F, here also direct edge is there. E. So now we are going to arrange the or insert the elements of D, adjacent elements of D, C, E, F into the queue. Now nodes visited sequence is D, marked now. Then we are going to use the queue as per the procedure, access the data which is available at the front end. So front end is having the C now. So peak pointer is indicating. Okay. So C is going to be deleted from the queue. Yes, it is deleted. Then we are marking that C as a visited. Yes, it is marked, and here that is visited and marked as a connected. Okay. Then it is colored for reference as a visited. Then nq nq the nodes adjacent to the C, okay, which are already not available in the queue, that is the unenqueued. Okay, so here C is not having any adjacent vertex, so simply you can delete that. No need to enqueue any vertex because it is not having any adjacent vertices. Then you select the next vertex in the queue, that is the E. So delete the E from Q. Yes, it is deleted. Then visit the E. Yes, it is visited. So now we reached the E. Then mark E is connected. Yes, mark E is connected now. Then enqueue the unenqueued nodes which are adjacent to the E. So for E, G is the adjacent node, only one adjacent node. It is unenqueued. Yes, you see, this is not available in the queue, and also it is not visited. Okay, so we can enqueue into the queue G, right? After that, we are going to access the next element from the queue is F. So F is going to be deleted. Yes, it is deleted. Then visit the F is marked visited. Then mark F is connected in the table for reference. Yes, it is connected. So now F is also marked as a colored for our reference. So now find out the adjacent nodes to the F. For F, adjacent node is C, but C is already visited. So no need to add that into Q. Okay. So now we will take the q. So q is having the peak element. Peak means element which is available in the front end. Okay, so we are accessing that. We are deleting that g from the q. Yes, it is deleted. Then visit the g. Yes, it is marked as a visited, and also mark as a connected. Yes, it is connected. Now find the adjacent elements. For g, adjacent elements are D and H. So here in the D and H, D is already enqueued. Okay, so we should enqueue only the unenqueued data into the queue. So only H is unenqueued. So we are going to enqueue. Enqueue means inserting into the queue. So we are inserting that H into the queue. After that, we are accessing here H. Actually, H is available here. So now H is going to be deleted. Then visit the H is as a visited, and mark that H is connected. Yes, marked H is connected. Then find the adjacent nodes of H which are unenqueued. Yes, H is having A and B, both are unenqueued. Then A and B is inserted into the queue. Once H is deleted, then this location will be empty. So A is stored in the 0th location, right? Then we are accessing the front element of peak element from the queue. A is available there. Then delete the A. Yes, it is deleted. Then visit the A. Yes, it is marked as a visit, and also marked as a connected, right? Then we are finding the unenqueued adjacent nodes to the A is having the B, but B is already queued. It okay, already available in the queue, already queued, so no need to insert again. Already it is inserted in the queue. So we are moving to the next step. The next step is queue is having a peak element is B. So now we are accessing the B and delete that B from the queue. Yes, it is deleted. Visit that B is a sequence of nodes visited. Then mark that B is visited. Yes, it is also marked. Now find the adjacent nodes to the B. So for B is not having any adjacent nodes, so simply move to the next step. The next step is now we are accessing the queue. Accessing the queue, but queue is empty. Once the queue becomes empty, then that means the graph nodes all are visited. Okay, so all the nodes in the graph is visited or connected. That is the meaning of the queue becomes empty. Then you can stop the algorithm. The here nodes are visited in the sequence of D, C, E, F, G, H, A, B. The table also shows all the nodes are connected. The time complexity for breadth first search is here order of v plus e. That means we are accessing all the vertices in the given graph, and we are finding the shortest path by visiting the edges. We are calculating by using the adjacency matrix or adjacency list. Thanks for watching.